You might already know this from other mathematics courses, but Section 8.1 in trigonometry talks about complex numbers. So if you know this, you may not need to listen to it all. But our sets of numbers start with not pulling that down and putting it back up. Gee whiz. There we go. Once again, our sets of numbers start with the natural numbers. It's a double strike N. It's like counting numbers. 1, 2, 3, 4, 5, 6, 7. If you add 0 to that, to the 1, 2, 3, etc., you get something called the whole numbers. Double strike W. If you add to that the negative, the opposites of the naturals, then you get the integers. And perhaps this is just a fancy I, but it looks to me like a Z. Double strike. So you could say Z integers and you'd know how to speak French. Anyway, up from that, all the fractions, 1/4, 0.9, 0.999, all those fractions together with the integers, and that's together with the whole numbers, we get what we call the rational numbers. And they use a double strike Q for that. Don't know why that is. Separate from that set is all the numbers that are a little strange. Square root of 2. Pi is in here. There's a delta called Feigenbaum's constant. E is Euler's constant. All those numbers that when you write them as a decimal neither repeat nor terminate. All rational numbers either repeat or terminate. And so these are irrational. It's a double strike Q prime. That's what makes up the set of real numbers. You don't add anything, you just put those two together, and you get the real numbers. Now, if you want a number that looks like A plus BI, you could say A and B are elements of the reals. You could say, aren't those real numbers? Yes, they are. If B equals 0, then this part, they call this the imaginary part, disappears and you just have A, which is the real number. But suppose B is not equal to 0, and suppose we define I as the square root of a -1, we can now find square roots, and we put these together with the real numbers, and we call these the complex numbers, a double strike C. When B is not equal to 0, these are called, I guess, complex or imaginary numbers. If it's just the A, then it's real numbers. If you have A0, then you've got to just BI, which is then a pure imaginary number. I don't know what they mean by pure. So, you've got some situations, but now you've got a set. This is a huge set. The real numbers are nice, and we usually focus on those because they have properties which we call the field properties, which we won't discuss here. The real numbers are a field, but the complex numbers are not, and that's why we usually say, okay, the real numbers are the biggest field we know of. If we want to do complex numbers, you're going to have to tell me. And so right now, we're going to do complex numbers. So, a couple of things. 1 plus 2i is how we usually write complex numbers, not 1 plus I2, although that's correct. It's not the nice way that a mathematician would write it. But a mathematician would write 1 plus I square root of 2, not 1 plus square root of 2i. And the reason for that is we want to make sure you know that I is not underneath the radical. It is outside the radical. So, also don't leave anything, any square root, really it's any even root, but square root's what we're going to use mostly here. No square root with a negative can be left with that negative. You should write it as, because this is really the square root of a -1, times the square root of 5. So the square root of negative 1 is I, square root of 5. Don't leave any negative underneath the radical. The index, once again, could be any even number, really. That could be that. And if you see that, you can think of what I like to say is pull your eye out. Don't really do that. I should not have any other power except for 1 also. Why is that? Well, because I to the first power is, of course, I to the 0 power is 1. Anything to the 0 power except for 0 is 1. I to the first power is I. I squared, defined as negative 1, because now we're squaring the square root of negative 1, but the negatives don't cancel in this case. I cubed is a negative 1 times I, so it's just a negative I. And what you'll see is I to the 4th is equal to a negative I, what I cubed is, times I. But that's a negative I squared, and a negative I squared is a negative 1, or the opposite of a negative 1, which is 1. And so you move back up to this spot. I to the 4th, I to the 5th, I to the 6th, I to the 5th, I to the 6th, I to the 7th, and then you move back up, I to the 8th, etc., etc., etc. So what is I to the 2020 power? Well, all you need to do is find out the multiple of 4 it is. And all you really need is the remainder. Because if you think about it, 7 divided by 4, divided by 4, doesn't go 4 times. It goes 1 time, times 4, with a remainder of 3. 7, I to the 7th is I cubed. So you really only need this part. Now, how do you do I to the 2020? Well, you can do the whole thing, but you never use this quotient. All you use is the remainder. So you don't really need the entire quotient. And for dividing by 4, you only need the last 2 digits. So what is 20 divided by 4? Well, that's 5 times 20. Remainder, 0. I to the 0 is 1. I to the 2020 is 1. So now you know how to take care of anything. The exponent for I, all it needs to be is a 1. So we can write these as A plus BI. The A without the I is called the real part. The BI is called the imaginary part. If two real numbers are equal, many times we'll say this is, say, z sub 1. And z sub 2 may be equal to c plus di, another complex number. We use z's an awful lot for complex numbers instead of x's. If z sub 1 is equal to z sub 2, then what do we know? Well, a plus bi has to equal c plus di, which really means the real parts are the same, and the imaginary parts have to be the same. So a equals c and b equals d. So how do you add or subtract? Well, let's see. If we have 1 plus 2i, and we're adding that to a negative 3 plus 4i, all we do is add the real parts, 1 and negative 3, so you get a negative 2, and add the imaginary parts, 4 and 2 is 6 i's. That's the sum. The difference is the same thing. Let's do it without rewriting it. 1 minus a negative 3, so that's really a positive 3 and 4. 2 minus 4, so now you get a negative 2i. So addition and subtraction is just combined, sort of like terms, the real parts and the imaginary parts. What about multiplying? Let me move this back down again. Looks like I keep messing that up. So to multiply, say 1 plus 2i, and we're going to multiply negative 3 plus 4i. Now you use FOIL, but you may not have to use it in that order. First times first, it's a negative 3. Let's do then last times last, because this is 8i squared. And then you do the inner product, a negative 6i, and the outer product, 4i. And now you combine like terms. Remember, I squared is the same as a negative 1, so this is not 8. This is negative 3 minus 8, or a negative 11. Negative 6, positive 4, so negative 2i. So the product of those two is like FOIL, but it's first, last, inner, outer, FLEO or something like that. What about division? Division is interesting because you never divide. So if you take 1 plus 2i and you negative 3 plus 4i, and you want to divide that, what do? You don't divide, you multiply. You multiply by the conjugate of the denominator. So what's the conjugate? Well, the conjugate is the same numbers except subtraction between. So if this were a negative 4, this would be a negative 3 minus a negative 4i, which is really plus. So the conjugate, all you do is change the sign of the second term. If it's plus, make it minus. And now you perform the multiplication just like you would normally. Let's see, this is 1 times a negative 3. 2i, negative 4i is negative 8i squared, but that makes it a positive 8. Over, this is negative 3, that's positive 9. 4i times, then 4i is, or negative 4 is negative 16i squared, so it's positive 16. Remember, we need to do the inner product and outer product too. So this is negative 6i, and this is a negative 4i. But this one is a negative 12i and a positive 12i. They cancel. So the denominator is just 25. The numerator is negative 3 and 8 is positive 5. And the negative 6, negative 4 is a negative 10i. Now, usually you want to reduce these, and perhaps you can see it easier by doing 5 over 25 minus 10 over 25i. So 5 will go into 5 once, into 25 5 times, and 5 will go into 10 twice, and then 25 5 times. So this is one way of writing that. You could just make sure you divide everybody by 5. You have to do it for everybody. 1 minus 2i over 5. Same thing. So, add, subtract, multiply, and divide. One last thing. Notice, then, that we were able to factor a squared minus b squared before. This is called the difference of two squares. And you factored that into the sum and the difference of their square roots. But you were always told you couldn't factor the sum of two squares. Well, if you allow for complex numbers, you can factor the sum of two squares, because now you can use the I to change that into a positive. So it is now a plus bi and a minus bi, because first times first, a squared, last times last, positive b squared I squared, inner product plus abi, outer product minus abi. So those cancel. But I squared is a negative. I'm sorry, this should be a negative here. Gosh, I'm way ahead of myself. bi times a negative bi, negative b squared I squared. But because I squared is a negative 1, this should be plus b squared. So you can factor the sum of two squares. You just need to use your eyes. Okay, let's do some examples from section 8.1. Number 20, we're supposed to identify this square root of a negative 36 as real, complex, pure imaginary, or non-real complex, or maybe a combination of those. Remember what that means. If we have a plus bi, then if it's real, it would just be the a. There would be no I. Complex has to have an I in there. It could be a plus bi. It could be just bi. But if it were bi, then it would be pure imaginary. And non-real complex is a plus bi too. So let's make sure this is clear. A real number is also a complex number. So this real number, oh my gosh, I did it again. See if I can not do that. Okay. So this real number is also a complex number. This is a complex number because it's got both a real and imaginary part. This is a complex number because it's got the I. A non-real complex number is a plus bi. So I guess complex is sort of, that's also, complex is sort of a generic, anything, I guess, works for this. Because everything in every set that we're talking about, at least for these numbers, is a complex number. So all of them are complex. Some of them are also real, just real. Some are pure imaginary. Some are non-real complex. That needs that I in there. So what is square root of negative 36? Well, remember, I said when you do this, you got to pull your I out. No square roots and negatives. So that's just the square root of 36. But I know the square root of 36, that's 6. And I'll put that first. So 6i is really the bi part. So this is complex, because they all are. And even better, pure imaginary. So what about, let's see. Let's rewrite this number 28. Rewrite this without all these negatives. The square root of a negative 80. Well, let's see. That negative's outside here. The square root of a negative 80 is I square root of 80. Pull your I out. So this is really a negative I square root of 80. But hold on. Maybe I can pull some things out of that 80. Let's see. That's 2 times 40, which is 2 times 20, which is 2 times 10, which is 2 times 5. So I can pull out a 2 and another 2. So I can pull out this 4 and leave behind 5. Now let's put it in the right order. This is probably the right order. The opposite of I, 4I should be maybe better. Square roots of 5. Maybe that's better. This one's a little harder to determine. Okay. How about number 40? Number 40 is find each product or quotient, and we have the square root of a negative 12 times the square root of a negative 6 over the square root of 8. Okay, first of all, got to pull your I out. I square roots of 12 times I square roots of 6 over the square root of 8. And now we got to figure all these square roots. Let's see. 12 is 2 times 6, which is 2 times 3. So I can pull out a 2. So this is really 2I square root 3 is left. Okay. For 6, well, that's only 2 times 3. That doesn't give us anything to pull out. So I squared of 6 is it for that. Now, what about 8? That's 2 times 4 and 2 times 2, so I can pull out a 2 and leave a 2 behind. So this is now, pull out a 2, but there's no I because it's not negative, it's just 2, and leave behind a 2, 2 square roots of 2. Okay, I times I is I squared, or negative 1. So we have 2, but it's a negative 1 because of I squared. The square root of 3 times the square root of 6 over 2 square roots of 2. Well, those 2's on the outside cancel. And this is then 3 times 6, or the square root of 18, over the square root of 2. But hold it. Gosh, I'm running out of room here. This then is the square root of 18 over 2, or 9, the square root of 9. But hold it. Square root of 9 is 3. My gosh. Well, at least I got 4 steps. Well, I think the add, subtract, and multiply are not too hard to do. So I'm skipping ahead to the divide problems. Remember, when you divide, you don't. You look at the denominator and multiply by its conjugate. And all you do is change that middle sign. If it's negative, make it a positive. If it's a positive, make it a negative. And you have to keep this the same, so you've got to multiply both numerator and denominator by this. See, last time I ran out of room. Negative 3 and 2 is negative 6. 4i and I is positive 4i squared. Now the inner product, 8i, and the outer product, negative 3i. That's our numerator. Now there's a shortcut to this denominator, but perhaps you need to go through it a few times without that just to see. 2 times 2 is 4. Negative I times positive I is a negative I squared. Inner product, negative 2i. Outer product, positive 2i. So negative 2i, positive 2i, those will cancel. The inner and outer product should always cancel. when you multiply by the conjugate. So, this is now not 4i squared, but because I squared is a negative 1, this is a negative 4. Negative 6 and negative 4 is a negative 10. 8 minus 3 is positive 5i over, well, remember, this is I squared is a negative 1, so minus a negative 1 is 4 plus 1. So now we got negative 10 plus 5i over 5. Remember, when you divide, you have to divide everybody by the same thing. If that doesn't work, you can't do this. Divide negative 10 by 5, we get negative 2. Divide 5 by 5, we get positive 1i. And divide this 5 by 5, we get positive 1. So it is really just negative 2 plus I. Well, we've already done the seniors, I to the 2020 power. The juniors graduate in 2021, so I to the 20, I guess the juniors from last year. But I to the 2021 power, remember, all you take is the last two digits, divide by 4, goes 5 times remainder 1. This is I to the first, or I. Take the 22, divide by 4. 5 times 4 is 20, remainder 2. This is I squared, or negative 1. Those are your final answers for those types of problems. So I think you should be able to do all those problems that are covered for complex numbers at the end of the chapter. We're just asking you to do odds, I think, in this case. Okay.